We're going to talk about how the particles in a crystalline solid are arranged. So the term crystalline lattice refers to the regular arrangement of atoms within a crystalline solid. They could be ions as well, but we're going to talk about atoms first. The particles are going to combine in a way that minimizes their energy. So this is an example of a crystalline lattice. Each of these circles represents a point of the lattice that's occupied by an atom, an ion, or a molecule. So each of the circles is an atom, and that's a point in the lattice. And so here we're seeing we can draw a square right here, and if we take that square and we repeat it over here, and we repeat it down here and over here, by repeating this one square in every dimension, we get the entire lattice. So this is this unit cell is the smallest piece of the lattice that we can repeat over and over again to get the entire lattice. If you go smaller than that and you repeat it, you're not going to get the same lattice.
So you not go diagonal?
We're not going diagonally. Well, I guess it depends on how you think of it. If you think of taking this and repeating it diagonally to that one, then that one might be okay.
I just mean because you have like you could form the square of 4 if it's in a diamond shape.
Oh, forming it that way? No, we're not going to do that. Because that does not match up with the faces of the actual crystal.
Gotcha.
Yeah, so then you'd end up with half triangle things like we have in Reedley on the streets.
Is this based on just like microscopic observations?
Well, we know from X-ray crystallography what the spacing is of the different particles. And so that's a big part of how we know what these things are doing. So this is a two-dimensional representation, but of course the solids are three-dimensional. So these are actually cubic unit cells. So the unit cell is a cube. In 2 dimensions, it's a square. So the unit cells we're going to look at in this section have all of the particles being identical, but they're going to sometimes be colored differently. And that doesn't mean that they're different types of atoms. It just is to help us understand what we're looking at, because it's kind of hard to represent these three-dimensional things in 2 dimensions on the screen. A couple of terms we use: coordination number and packing efficiency. Coordination number refers to the number of atoms that each atom is in direct contact with. So how many close neighbors, how many touching neighbors does the atom have? Packing efficiency is the percentage of the entire volume of the unit cell that's actually occupied by the atoms themselves. So if you have high packing efficiency, that means there's less empty space within the cell. A lot of my analogies come from the fruit industry, because I live in Reedley and it's a big deal there. So fruit packing, I mean, you can imagine this even if you've never seen a packing house. You've got a whole bunch of oranges and you need to put them in a box, right? You want to pack them in the most efficient way so that they'll take up the smallest amount of volume when you ship them, right? And so there are some ways that you can pack spheres that will leave a lot more empty space. So packing efficiency tells us something about how much empty space there is. If you have a higher coordination number, you're going to end up with better packing efficiency, meaning there's less empty space. So this is an overview table from your textbook showing 3 of the cubic cells. There's the simple cubic cell, body-centered, and face-centered cubic. And this chart is a nice reference for doing homework problems. But we'll go over all of this in detail. So the simple cubic cell has 1 atom at each corner. So this is the center of an atom, and the center of an atom, and the center of an atom, and the center of an atom. And 3-dimensionally, it looks like this. So we're just going from the center of each atom. And it just makes a cube. We see that the atoms touch each other along the edge of the cube. And so we can talk about how long is a side of the cube in terms of the radius of the atoms.
Is that the crystalline lattice structure of sodium chloride?
I don't think so.
Okay.
I don't remember off the top of my head. We will look at specific examples in the next section. For now, we're just talking generally. So if the radius of the atom is r, then the length of the side is twice that. So the length of the side is 2r. And each of these cubes contains one atom. Might take you a minute to think about that. This guy at the corner, that's 1/8 of an atom, right? And this is 1/8 of an atom, and 1/8 of an atom, and 1/8 of an atom. And there's 8 of those. So if you took all these pieces apart and put them back together, you could get one atom. It's parts of 8 different atoms, but in that volume there's one atom. Yes?
So, why can't you just put one circular atom in the box and save that?
That's a good question. Why can't we just say, well, here's our cubic cell, it's just the sphere? How does this sphere relate to the sphere next to it?
Touches it?
Well, if we just represent it like this, then we don't know that they're lined up next to each other and not in a pattern like this, which is different, or that one. Okay, it's a good question, but that's why. So if we're talking about coordination number and packing efficiency, coordination number looks at one atom in that lattice and says, how many atoms is it touching? Well, it's touching 1 on each side, so a total of 6. So this guy is directly touching 6 other atoms. We've kind of expanded this so that we can see, otherwise all the spheres block each other. The packing efficiency, which you could calculate, but we're not going to mess with that. The packing efficiency there is 52%. 48% of that cube is actually empty space. That's not very efficient.
But light.
Yeah, it's going to be lighter.
Carbon fibers.
And the density of the solid is going to be affected by how the particles are packed together. If you pack with 52% efficiency, you're going to have a lower density than if you pack it with, say, a 78% efficiency. The next unit cell we'll talk about is the body-centered cubic. So here there is a body, an atom in the middle of the cube. And then on each corner, again, we have 1/8 of an atom. So this cell has 2 atoms in it. That whole one in the middle plus the 8/8. These do not touch directly across the length of the side, do they? There's a gap in there because this guy's holding them apart. And they don't touch diagonally on a face either. They touch diagonally across the whole cube. So from one corner of the cube to the other corner diagonally across. And so there's the geometry if you're interested. I'm not going to go over it. The length of the side is equal to 4 times the radius of the atom divided by the square root of 3. This atom in the center is actually the same kind of atom as the purple ones. We're just drawing it as a different color so that we can see it better. Any questions about that one? When we look at coordination number and packing efficiency, again, we need these colors to help us see what's going on here. Here, looking at one atom, it is actually touching 8 atoms now instead of just 6. So higher coordination number, and the packing efficiency is higher at 68% instead of 52. Yes?
So if we stacked an orange directly on top of another orange, you're saying we would have less, you could put less oranges in a box than if we were putting in between each other?
Yes. Yep. And that's something, you can go home and play with marbles or oranges or, balls or something, and you can demonstrate that for yourself.
They all have the same atomic radius?
Yes.
So these are all like
Yeah, they might be iron
basically?
atoms or something. And the purple ones are iron atoms, and the gold ones are iron atoms.
Alright.
They're not different.
So it would change if there were different sizes?
Yeah,
They'd be
and we'll talk
completely
about that
different
in the
lattices.
next section. What happens if they're different sizes?
So I know they're the same atoms, but besides the surface ones, every single one of those purple ones is potentially a gold one too, right?
Yeah, depending on where you make the cube.
Okay.
Yeah.
Gotcha. And that's why they touch 8.
Right. So if you take this cube and shift it over, you could make a purple one the gold one, and the gold ones would end up being the corner ones. You could shift it over half an atom like that. So higher coordination number, higher packing efficiency. And then there's the face-centered cubic. So here, the side of the unit cell has the face is centered in the middle of an atom. So there's half an atom here, half an atom there, half an atom on the other side, half on that side, half on the top, half on the bottom. How many atoms is that? 3. Here's 1, 2, and then there's on the other side 3, 4, 5, 6 halves. So there's 3 gold ones, and again we have the 8th of the purple ones, and there's 8 of those. So this has 4 atoms in the unit cell.
I'll tell you
And
how many atoms make up that structure.
This contains, if we,
I get what you mean.
okay,
I
okay,
got you.
yeah, it has parts of more than 4 atoms. But if we took all these parts and reassembled them as atoms, it would be 4. Yeah.
How dependent is this on electron geometry and the orbitals?
This does not depend on electron geometry or orbitals or hybridization or anything like that, because we're not talking about covalent bonds.
So this is just completely different.
This is completely different. So this would be intermolecular forces from individual atoms, or possibly molecules, or ionic bonds between ions, those sorts of things. In this one, we have direct touching diagonally along the face of the side. And so again, you can do the geometry. That's not the point of this lecture. But this side, L, has a length that's equal to 2 times the square root of 2 times the radius of the atom. So we've got this information about the length of a side. And so from that, we can calculate the volume of the cube if we want to, right? Here, the packing efficiency is 74%. So the last one was 68, this one's 74, and the coordination number is 12. And this gets harder to see. It's like random dots. And you look at them for a while and they start to swim around. I would go with just believe me on that one. So coordination number is 12. Pardon me?
I said this is 74%, so it's getting
Right.
more efficient.
Yeah, the higher the coordination number, the higher the packing efficiency. Could you ever get to 100% packing efficiency?
The edges would be so sharp.
Not packing spheres. If you're packing spheres into a cube,
You can't
there's
get-
always going to be empty space.
What's the highest possible?
I think 74 is about as high
That's
as
the
you can get.
maximum? Unless you have like varying sizes, so you put like the little balls in the corners. And, like, the
Yeah,
big
but then
balls in
that's
there.
really a different kind of question.
And that's the next
Still
chapter.
couldn't achieve them.
It's the next section.
You can get close with different sizes. So get closer and closer.
And so there's whole branches of chemistry that are very, very interested in all of this and how things pack together and how you could get them in there closer and what exact shapes everything is. And we're just like, skimming the surface.
What would happen if we could achieve something though to 100% like that?
Well, because of the shape of the atom being spherical, it's impossible.
Could you compress an atom and like change its shape?
When you get covalent bonds between atoms, then you could get them packed more closely,
But you won't.
but you're still not going to get 100%. Yeah.
So lead is probably that structure then?
I don't know off the top of my head.
I was just thinking because
So
you use
dense.
lead to block
Right.
radiation.
So dense.
Lead is one of the densest elements, but it's not the densest.
It's not plutonium.
But plutonium, I don't think, is the densest either.
The octium.
No, density does not necessarily correlate with atomic number.
Oh, that's right.
Yeah. Okay, so we could answer a question like this. And you do not need to memorize the coordination numbers, the packing efficiencies, or the length of the side in terms of R kind of thing. But we will definitely see some homework problems like this. So chromium crystallizes with a body-centered cubic unit cell. The radius of the chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. You're like, what? What?
Wait, I'm working on it.
Okay, this is the kind of problem that a successful Chem 1A student should be able to solve. It requires some thinking, right? You can't just say, oh, we had an example like that and go and copy and follow a pattern. You have to be able to think it out. Well, body-centered cubic unit cell, that's a clue. Let's go back and look at what we have for that.
2 whole.
So there are 2 atoms in a cell, and the length of the side is 4/3 over the square root of 3. Oops, that's not what I meant to do. So let's just write that information down. 2 atoms per unit cell. Length of a side equals 4r over the square root of 3.
See, but now, if we don't have that, then how are we going to be able to do this problem? Like, I can't just...
Well, you need this, and I don't expect you to memorize that.
Probably.
I just said that.
Now it's a simple math problem.
It's a math problem. It's a word problem. So here, 125 picometers, what are we going to call that?
Radius.
Yeah, that's the radius. Because this cubic unit cell, this body-centered cubic unit cell, the length of the cube on a side is in terms of the radius of the particles. And they told us what the radius of the particle is. Now, it says calculate the density. So, what does density equal? Mass over volume. So what we need is the mass divided by the volume. Density is a property that does not depend on how much stuff you have. The density is constant, whether you have a little bit or a lot. So what we're going to do is we're just going to choose an amount. I'm going to choose 1 unit cell, because I think that's going to be the easiest. So we're going to say, well, let's look at 1 unit cell. Can we calculate the mass of 1 unit cell? Yeah, because we know there's 2 atoms in the unit cell. Do we know how much the atoms weigh? Yeah, that's on the periodic table. So let's figure that out. So for 1 unit cell, I have 2 atoms per unit cell. I'm going to call that UC. Well, periodic table shows me 51.9961. What does that mean?
Just call it 52.
We're not going to call it 52, no.
3 sig figs.
But the mole,
per mole.
that's a molar mass, so that many grams per mole, right? So I've already forgotten the number, 51.9961 grams per mole. Avogadro's number. A mole is Avogadro's number of atoms. That was awesome, by the way. 6.022 times 10 to the 23rd atoms. Okay, so I've got the unit cells canceling and the atoms canceling. This is going to be the mass of 1 unit cell. It's got 2 atoms in it. I knew I forgot something. I forgot my calculator. That's okay. I've got my got my phone. So 1 times 2 times 51.9961 divided by 6.022 times 10 to the 23rd, 1.72. We should probably have at least 4 significant figures here. So there's 4, and I'll throw 2 extras in, times 10 to the minus 22 grams. That's really tiny. Is it okay that it's really tiny?
It's 2 atoms.
It's 2 atoms. It better be really tiny. Okay, so that's the mass. So I'm going to put that in here. 1.7268 7 times 10 to the minus 22 grams. Now, we need to calculate the volume. Again, we picked 1 unit cell. We need to calculate the volume of the unit cell, and the unit we want here is cubic centimeters. This is in picometers. I think it's easier to convert the unit before we cube it, because we're going to end up cubing it, and then things get messier. So what I'm going to do here is I'm going to say, well, 125 picometers, instead of writing the P, I'm going to write what pico means. Remember what pico means? Negative 12. So that's 125 times 10 to the minus 12 meters. 10 to the minus 9 is nano. Pico's the next one, and it goes by 3s. Not proper scientific notation, but it still works, and it's easy. How do we convert that to centimeters?
Centis to the -2, so meters to the -10.
So we want centimeter up here, and we want meter in the bottom, so those cancel out, right? And then we say, well, centi means 10 to the -2. I have centi up here. I want to put 10 to the -2 on the other side. There are other ways to do it. If you're good at those ways, you go right ahead. But if you're not careful, you can also make silly mistakes doing that. So 125 times 10 to the minus 12 divided by 10 to the minus 2. So 1.25 times 10 to the minus 8 centimeters. Somebody with a real calculator get that too?
What did you get? I'm sorry.
1.25 times 10 to the minus 8.
Probably don't have mine in scientific use.
Here I have a big unit, and this number is smaller than the small unit where the number is bigger. The most common mistake is that you move the decimal place in the wrong direction.
Yeah.
Okay. So if this is the length of a side, then the volume equals the length cubed, right? So volume equals the length of the side cubed. So I'm going to cube this whole thing. So I'm going to take 4 times my length, 1.25 times 10 to the minus 8 centimeters, divided by the square root of 3, and I'm going to cube the whole thing. So that number times 4 divided by the square root of 3, and then cubed. I've never tried to do this on my cell phone calculator before, so let's see if I did it right. That should have 3 sig figs, 2.40, 0.056 times 10 to the minus 23rd. Anybody else get that? Okay. And that's cubic centimeters. That's crazy small. Is that okay? Yeah, because we're talking about 2 atoms, right? So it should be crazy small. So I'm going to stick that in here. 2.4056 times 10 to the minus 23rd cubic centimeters. So I've got 1.72687 times 10 to the minus 22 divided by 2.4056 times 10 to the minus 23. And I should have 3 significant figures in my answer, 7.18 grams per cubic centimeter.
2 atoms have the density of 7 grams.
2 atoms would have a density of 7.18 times grams per cubic centimeter. It's kind of hard to talk about the density of 2 atoms, though, right?
Yeah, so you're saying that 2 atoms will weigh 7 grams?
No. I'm saying that 1 cubic centimeter of atoms arranged in this pattern would weigh 7.18 grams.
Cube in that crystalline form.
Yeah.
Alright.
But the density, if I had a little tiny piece that was 1 centimeter on a side, or if I had a big piece that was a meter on the side or a kilometer on the side, the density is the same. Because as the mass increases, the volume increases too. And because they're divided, the ratio stays the same. And that's an important thing about density that a lot of students just don't quite have clear yet. Is that a reasonable density for a metal? Yeah. Because metals float. Do metals float? No. Metals sink in water, right? Exactly how a metal boat floats is something else. But a chunk of metal, that has to do with displacement, and that's physics.
Surface area.
Surface area, all kinds of stuff like that. And surface tension. But the density of a metal should be higher than 1 gram per cubic centimeter because that's the density of water, and so this is definitely in the right ballpark. So there's all kinds of questions that could be asked. They could give you a density and a type of unit cell and ask you what element it is.
Looking backwards.
Yeah, they could give you a density in the element and ask you what kind of unit cell it is. I mean, there's all kinds of different things that could be done. I know, right?
That's on our homework.
Pardon me?
Is that like on our homework?
I think so. I picked the homework a while ago, and so I don't remember exactly what's on there, but it seemed good at the time. So any questions?
Sure, I'll have some things.
Yeah, I'm sure you will. Okay, so that's one way to look at crystal packing or atom packing. Another way is to think about stacking atoms up in layers. And this relates a little more to like packing oranges. So the simple cubic layer is where you put 1 layer of spheres and the next layer is packed with atoms directly above each other. That is not how marbles or oranges are going to naturally pack, but you can pack them in that way. And so when we pack them like this, where the layers are exactly on top of each other, that's where we get that simple cubic unit cell. There's a lot of empty space in here. Not the most efficient way. More efficient is to offset the second layer. And this is what happens naturally when you start to put the second layer in. The second layer wants to sit in these little divots, in these little indentations between the first layer, right? And so it kind of sinks down as opposed to sitting on top of the first layer. So layer B is offset by half an atom. It's scooted to the left half an atom and down half an atom, so that it sits in the little holes. So we have layer A and layer B. What's called hexagonal closest packing is where you've got that first layer, the second layer is offset, and then the third layer is identical to the first layer. So the spheres in that third layer are directly on top of the first layer. And so that gives you an A-B pattern.
Is that pretty efficient?
It's pretty efficient. This is a packing efficiency of 74%. Coordination number of 12. In this structure, the unit cell is hexagonal. It's not a cube. So this is the unit cell. I know, right? You thought the other one was complicated.
It's the same thing, just more size, actually.
Yeah, it's the same idea, but now instead of this being a sphere, cube, it's a hexagon on the one side, on the top and the bottom. And then it's like a rectangle on the sides. So that's called hexagonal closest packing. Yes?
Now, instead of returning to original position, what keeps it from just keep on moving more to the right and more to the right?
Well, it falls into that little indentation,
Mm-hmm.
right? And it's like stuck.
Well, let's say you have like, I don't know how to do that actually. So we'll just not ask it. I was like, I can't do a diagram like that.
So just to make sure, like, that there's 3 red circles,
Mm-hmm.
and then there's 2 halves of the blue, and then there's, the other 2 are coming from the 6 that are being around it.
Yeah. 1, 2, 3, 4, 5. I suspect that this has 6 atoms in the hexagon, but the book doesn't actually tell us that.
So, but the ones on top that are forming 6, that all comes together to form 1 then?
I think that all of this comes together to form 1. It's really hard to look at, isn't it? Yeah. And that's not something I'm going to quiz you on. I should figure that out, though, for next time, because that's a good question.
Wait, you think all the ones, the blue ones on top form 1 atom or something?
I think that this is half, and there's a half on the bottom, and there's these 3 red ones. So there's four atoms, and then I think, I'm just guessing that these edge pieces around the edge here and the ones around the bottom probably combine to form 1.
I think that makes sense.
I'm not basing that on anything but a kind of a gut feeling.
I think it's really hard to
It's hard to
put
look
into
at.
pictures because you have to have 1/6 of an atom, which how do you do that?
Yeah, that's tricky.
It's not 3D. If we had 3D glasses, you could like move it like in an interactive.
Well, see,
program.
this is, in one plane, this is a quarter of an atom, and in this plane, it's a quarter of an atom, and in this plane, I think it's a third of an atom.
Yeah, so
Yeah, and
the
that's
3
way
that
more.
form a third, and you put it on,
Yeah.
those are a third, and you connect them together.
That's what I think, too. Then there's what's called cubic closest packing. So we've got our first layer and our second layer, same as before, but now the third layer is offset from both the first and the second layer. So in this layer A, this ball, there's 1 in front and 2 behind. In layer C, there's 2 in front and 1 behind. So they're not directly on top of each other. Here we get an ABC pattern. And this also has a coordination number of 12, and it also has a packing efficiency of 74%. Because the coordination number and the packing efficiency go hand in hand. This is the same as the face-centered cubic, a different way of looking at it. So there's the face-centered cubic that we looked at before, and that would come from this arrangement of colored balls. And when we look at the layers, that's like looking at this on the diagonal of how they're stacked up together. And again, the colors are just to help us visualize what they're trying to show us.
Efficiency goes down on this stack here.
This one has the same efficiency as the hexagonal. So the cubic closest pack and the hexagonal closest pack have the same coordination number, same efficiency.
You know what it kind of looks like?
What?
Beer pong.
Beer pong. Yeah, like at 7-Eleven, they have all these nice little cups and the different colored ping pong balls and stuff, yeah.